Has anyone read the chapter? Chapter 11? Pretty readable, no? Okay. So what's emotion? What do you want emotion means? Don't look at the definition. What do you think emotion means? Yes?
So it's something you're feeling, like you're angry, you're mad.
So you brought up a good point. There is emotion and there's feeling. What is the difference between them? Is there a difference between emotion and feeling? Yes.
Well, you can feel like something that's cold, or you have a cold feeling, but it's not really an emotion.
Oh, that's a good point. Okay. Like a sensory feeling. Okay. Yeah, Victor.
Maybe an emotion will cause a certain feeling.
Okay, so you think like a feeling is like it goes under emotion. Emotion is something bigger.
It's a consequence of an emotion.
Okay.
What happens after?
Anyone else? Okay, so I'm not going to really come up with a definition. I mean, the book gives you one, but it's probably something that does include feeling, where feeling is a part of emotion. But emotion is also going to have a cognitive aspect to it, an action part to it, and the feeling part to it. Okay? And today we're going to talk about emotion and the biology of emotion as far as how the brain labels something that we physiologically feel into an emotion. Okay? And we're going to talk a lot about the activation of an autonomic nervous system that we talked about before, what are the two different parts of the autonomic nervous system? The sympathetic and the parasympathetic nervous system. Exactly. And what does the sympathetic nervous system do? Exactly. And then the parasympathetic nervous system? For what? Yeah, rest and digest. If we're going to use fight and flight, might as well say rest and digest. Okay, so there's been many different theories to explain why we emote. Why do we have emotions? Why do we feel these physiological changes and we label them as a certain emotion? So folk psychology, which is kind of like common sense, introspection, kind of like your mother-in-law interpretation of why your child is acting a certain way. So basically something that's not based on science, okay? Would say something like your feeling triggers some sort of changes in your physiology. So you feel something, you're sad or something, and then that will trigger changes in your autonomic nervous system. Okay? Scientific theory, so for example, let's begin with the James-Lange theory, which is in every single textbook that talks about emotion, would actually say something that's counterintuitive to this, and that is you get first autonomic reactions or changes, that is in the sympathetic and the parasympathetic nervous system, and as a result of these changes, you then get feeling or emotion. So it's the opposite, it's counterintuitive. Okay. And in the Cannon-Barth theory is that you actually are getting the autonomic nervous system changes and the feeling at the same time. And it's the brain that's mainly responsible for labeling this cluster of changes in your autonomic nervous system into an emotion or an emotional label. Okay? So sometimes taking advantage of, more specifically, the James-Lange theory, saying that if you're saying that emotions will have a certain cluster of autonomic nervous system changes, then each emotion is going to have its own cluster of or pattern of autonomic nervous system changes. And then you can catch someone lying by measuring these physiological changes and know if the person is lying. Okay, and that's how the polygraph works, and we'll talk a little bit more about that. And then more modern neuroscience, there's some hope for something like brain imaging to see if a person is lying or not. But before that, I want to just show you a schematic description of the three different theories we talked about. So first you have folk psychology. Something happens in the environment, a stimulus, or let's say a bang, and then you perceive that as something dangerous, and then that leads to a particular emotion, fear, because you heard a bang that's unexpected. And as a result of the emotion, so it's a cause and effect where the emotion comes first, fear, and then you get the autonomic nervous system changes, such as the heart rate races, your eyes dilate, and so forth. As opposed to the scientific theories, so let's begin with the James-Lange, because it's the oldest one, where you get a stimulus again, you hear the bang, you perceive that as dangerous, and then after you perceive that as dangerous, that evokes autonomic arousal, the heart rate racing, the eyes dilated, and as a result of that physiological changes in your sympathetic nervous system is interpreted as fear. So the two last steps there are reversed. Okay? And then the Cannon-Barth theory, it's not really a cause and effect for the last two steps there. They're actually happening at the same time. You get the heart beat increases, the eyes dilate at the same time that the brain is giving the label of fear. Does that make sense? Okay. So back to the lie detector polygraph. Let's see, do they work? Do they not work? Do you guys think they work? No? You think they work? Okay, well, let's see what science says. Okay, so basically with a polygraph or a lie detector, you're taking multiple physiological measures at the same time. Okay? You're basically surveying what the autonomic nervous system is doing by measuring the sweat glands, so how much the person is sweating, because presumably if they're lying and they're feeling anxious about their lying or guilty about their lying, they're going to sweat more. That's one variable that you measure. Also heartbeat. Is it accelerated? Is it decelerated? With the assumption that if a person is lying and again they're anxious or guilty about lying, that's going to speed up their heart rate. Okay? And the sweating is measured by skin conductance, and then also measuring the breathing. If they're lying or anxious, they're going to breathe much faster. So, and that's what the lie detector looks for. You measure all these variable, physiological variables, and note that all of them are measures of the autonomic nervous system. None of them are measures of the brain. Okay, so very much in sync with the James-Lange theory, which talks about the autonomic nervous system. Okay? Because remember, Cannon and Barth said that the brain gives the emotional label. Okay, well, according to the companies that make them, they're 95% effective. According to science that's unbiased and impartial, they're only 65% effective. Okay? Now, and the 65% effective is for someone who feels anxious and guilty about lying. But how about people who don't? Can you think of someone who wouldn't? What kind of person would that be? An example? Exactly. So a psychopath can lie without feeling anxious and guilty, and the polygraph will not pick up on that, which is probably the criminal you're interested in finding out that they're lying. Okay? So people like that who can just like fake lying in a way that they can control the autonomic nervous system, so you won't be picking up on the sweating or the breathing or the increase in heart rate. That person you won't be able to pick up whether they're lying or not. Someone with an antisocial personality, or also known in society as psychopath, sociopath. Okay, now modern science has some hope in terms of using PET scans, MRI scans, like actually pictures of the brain. Because we know from studies that someone who is on purpose lying, who's consciously lying, because somebody could be honest but not saying the truth. Does that make sense? Somebody could be honest but not saying the truth. And somebody could be dishonest and not saying the truth. So we're interested in the latter situation, when a person is consciously lying, that triggers some activation in the prefrontal cortex, which is, as you know, is very important for executive kind of mechanism and control of over behavior. Okay. there's also evidence that the anterior cingulate gyrus also becomes active when a person is lying. Now, I don't want to say that this is in the stage of science fiction. Okay, it's not. It's closer than that. But I also don't want to make it sound like we could use this today in courts and it has 100% reliability. We're not there yet. Okay, but there's certainly more scientific promise than in the lie detectors. Because the psychopath can't really fake brain activations. Okay, but in terms of the PET scans and the MRI scans, the reliability, does everybody know what I mean by reliability? Okay. So the fact that every single time you take the brain scans, it looks exactly the same. Consistency. So the reliability of these measures, the consistency of these measures is not there yet. It's not 100% reliable yet. And if you're going to use it in courts, you want it to be 100% consistent because you can't afford a 1% error rate, which we are way above that 1% right now as technology is the way it is right now. Okay, because remember the MRI, the imaging technology is not that old. We're talking about maybe early 90s. It's pretty young. Okay, but there's a whole field out there about the WEDS, neuroscience, and the court. So I went to this extremely interesting like neuroscience in the court symposium that was really interesting, where people had like a PhD in neuroscience and a law degree. I'm like, how long have you been in school, dude? Like, seriously? And it's like really interesting. So it's not that this is actually not used in the court. People have actually used this in the court to reduce their sentences. Okay? So, for example, there was a case in the court of a pedophile who, whose case was reduced, his sentence was reduced because they found that actually he had a tumor in a certain area in the brain, and that once that tumor was removed, that he was no longer attracted to children anymore. Okay? Now, I don't want to make the case that all pedophiles have a tumor. This is an extremely rare situation where that tumor caused this pedophile behavior. And then once the tumor was removed, the pedophilia was also removed. Okay? But cases like this have been, I mean, this, I don't want to make it sound like this is never used in the court. It has been used as adjunct evidence, but it's not going to make or break the case, if you will. And second thing is that MRI scanners are very costly and expensive, and so is PET scanning. So it's not going to be widely available, like a polygraph is very inexpensive compared to an MRI scanner. That's probably well over $1 million to keep every year or maintain. It's really, really expensive. And with a PET scan, you have to inject the person with a radioactive material, so they have to consent to that. So it's just a lot more complicated. But I think compounded with the fact that it's not 100% reliable, I think for now it's probably not going to make it or break it in the court. But I feel like in the future it probably will. Okay, so here's the 3 different variables, physiological variables in the polygraph that are being surveyed in essence to know what the autonomic nervous system is doing, with the assumption that that's consistent with the James-Lange theory, that different types of emotions or feelings are going to come with their own clusters of autonomic changes. So here we're looking at breathing rate, skin conductance for sweating, and the heart rate. And then on the bottom, we have what I talked about second in the previous slide, and that is the PET scans. Here we have an MRI scan showing activation in the prefrontal area that goes with conscious mind and the anterior cingulate. Okay, are we all cool with the James-Lange versus the Cannon-Board versus like what common sense says? Are we very clear about the direction of the arrow, cause and effect? What comes first? Okay, great. Okay, and then this amazing experiment that Schachter did in the mid-70s kind of changed things a little bit. Okay. And what Schachter's theory, which stems from a very important experiment that they did, argues that emotional labels are given to this non-specific feelings or physiological arousals. In other words, what that means is that clusters of physiological symptoms are not necessarily belonging to just one emotion. Like depending on what else is going on, what environment you're in, what kind of cognitive state you're in, that same cluster of emotion, that same cluster of physiological changes can be emotion A or emotion B. Okay? So the Schachter and Singer experiment that I alluded to just a minute ago shows that these autonomic responses, and when I say autonomic responses, I'm referring to the sympathetic and the parasympathetic nervous system, these changes do indeed are important. He's not saying that these autonomic changes are not important. They're very important, but not in terms of differentiating among emotions, but rather turning up the volume, if you will, of the emotion, making the intensity a little bit higher. Okay? So let's see what they did. Oops. They had these subjects come into the lab to fill out forms. Okay? And the subjects got a shot of epinephrine. Now, epinephrine is supposed to do what? Basically, adrenaline. What is it supposed to do? Speed up heart rate, absolutely. So basically, turn on what? The sympathetic or the parasympathetic? The what? Oh, I know both of them rhyme, and they have the sympathetic nervous system. Okay? So the increases in heart rate, the eye dilation. So basically what they did is they made everyone who came for the study have the same exact autonomic nervous system changes. Right? Okay? Now, so they're filling out applications, which is not really any kind of like emotion-evoking event. But what was an emotional evoking event is that they had Confederates that worked with the researchers, where half the group was exposed to a Confederate who was just frustrating, angry person. And the other half was exposed to a Confederate who was just a happy person. Okay? Right? So half angry Confederate, half they had a happy Confederate. The people who were exposed to the happy Confederate interpreted the autonomic nervous system changes that were caused by the epinephrine shot as I'm feeling elated and happy. The group with the exact autonomic nervous system changes, because they got the same epinephrine shot, interpreted what they were feeling as that they were feeling angry and frustrated. Okay? Does that make sense? Now, the group that did not face a happy or angry Confederate, they didn't feel either way, but they did notice that their emotions was more intense. Now, this information can then, in the future, when you're filling out forms again, will bring up a memory of that, and it might give feedback through a feedback mechanism, make the person either angry or elated, depending on which Confederate they faced. So I wanted, yes?
I'm confused. Where did they prove that the epinephrine actually caused a change in emotion? Because if you were exposed normally to a happy person or an angry person, wouldn't you feel that way anyway?
Absolutely, yes. But what they wanted to make sure of is that, so remember, they wanted to look at the James-Lange theory, yeah? And the James-Lange theory says, or claims that there's changes in the autonomic nervous system. And each emotion is going to come with its own patterns of changes. So each emotion, so basically there's going to be no pattern of autonomic nervous system changes or cluster of changes that belong to two different emotions. Yeah? So what they showed is that actually indeed there are. So you have the same exact autonomic nervous system changes because you controlled that as an experimenter, and they wanted to have that control by administering an epinephrine shot. And these autonomic nervous system changes, identical ones for both groups, were interpreted as two different emotions. Can you see that?
I do. I just feel like maybe it's more complicated than just like one chemical.
Oh yeah, no, absolutely. Yeah, absolutely. But typically in an experiment, you control one thing at a time. But what they did add something that is really important is that the cognitive state, the environment you're in, that's going to be important in interpreting what's going on. It's not just going to be like, okay, heart rate plus the eye dilation plus this, that equals fear and only fear.
Yeah.
Yeah. And that explains why it's very difficult if you're doing a lie detector test to know the difference between a person lying or just anxious.
Right.
Because there's so many overlapping features between them in terms of the heart rate and so forth. Okay, but so the Schachter-Singer experiment, I want to know, is it consistent with the James-Lange theory or not? So basically, there were two main findings. Never mind. Okay, I did not intend for the green check mark to be there. I wanted you to come up with that. Okay, but let's pretend that it doesn't exist. Okay, so all the subjects who were administered the epinephrine injection, they all reported that they had more intense emotions. Okay, would that be consistent or inconsistent with the James-Lange theory? And think about it. So basically, the turning up of the autonomic nervous system also turned up your emotional intensity. So Victor, you're nodding yes?
Because they increase the physiological changes and the emotion is more intense.
Absolutely. So, okay, so that finding from the Schachter-Singer experiment is indeed consistent with the James-Lange theory. Now, the finding that all subjects experience the same autonomic nervous system, but yet they reported different emotions, that is not consistent with the James-Lange theory. Can everyone see that? Okay, if you can see that, then you really understand the James-Lange theory. Okay. Then somebody else came up with a theory of emotion that's very consistent with like colors, kind of like the theory of colors in terms of intensity, in terms of how colors come in opposites, and in terms of how we have basic colors and then a combination of the basic colors, you can make more complicated colors. So based on these same principles of colors, somebody came up with something similar for emotions. Okay, and that's Plutchik. He suggested that we have 8 basic emotions, and they come in opposites. So basically, we have 4 pairs of opposites. Joy versus sad, affection versus disgust, anger versus fear, and expectation versus surprise. So by saying basic, what we mean by that is that all cultures and everybody has these 8 basic emotions. That you don't have to be taught these emotions, that they come when you're born. And any other kind of emotion that you have that's not one of these 8 ones is basically a combination of any of the 8 basic emotions. The same way we think about color. Now, there is agreement over that indeed there are basic emotions where a person doesn't learn, that it's biologically programmed. There's definitely agreement over that. But there is a lot of disagreement and debate over, well, how many basic emotions do we have? Do we have 6, 7, 8? Okay? So, you have the level of intensity, from high to medium to low. So the ones I just mentioned were the ones in the medium panel. Coming in opposites, like happiness versus sadness, fear versus anger. And then if you turn up the intensity a little bit, then you get ecstasy versus grief, as opposed to happiness versus sadness. You get terror versus rage, as opposed to fear versus anger. You turn down the intensity a little bit, you get contentment versus pensiveness instead of happiness versus sadness, and apprehension versus annoyance versus fear versus anger. I'm just giving you a couple of examples. Okay? Does that, yes?
So what he was saying is that, so that any other emotions, anything else that we feel is just a combination of either of those?
Yes.
Either intensity too?
Mm-hmm. And any emotion that's not one of the 8 emotions here is going to be a combination of them. It could be a combination of 2 of the basic emotions, of 3 of the basic emotions, of 4 of the basic emotions, of all of the 8 emotions. Okay, so for example, depression is really not an emotion. It's a cluster of many, many different things, and it's a clinical diagnosis. People use it very loosely, and it shouldn't be used very loosely, because it actually can affect how you act. But it's a combination of many of these things. Okay, does that make sense? So I'll let you look at that for a second. Okay. So one way to kind of tell if we have basic emotions is to look at facial expressions and to look at common facial expressions across cultures, and also the interpretation of facial expressions across cultures. Okay? So here's different men, male, female, different countries displaying 8 basic emotions. Okay? So there's, I think the happiness one is like the easiest one to tell across any culture. If somebody's smiling, you know, it doesn't matter where they are in the world, you know they're happy. Okay. And the one who's surprised is really surprised in this picture. Okay, and then I want to point your attention to the last 2 here. Okay. The one, contempt and embarrassment, and remind you that in the previous slide, the one that the theory where it was built kind of like in the colors and how, that we had affection and expectation. So back to my point that there is indeed agreement over the fact that we have basic emotions, but there's disagreement about how many we have and exactly which ones are they. So the first 6 are the same identical ones to the ones that, that we had in the previous slide. Okay? The last 2, contempt and embarrassment, are different. So in the previous one you had affection and expectation, and did not have contempt and embarrassment. Okay? So these basic emotions are out of the work of Ekman. Okay? And Ekman did enormous amount of work on facial expressions and basic emotions going across different cultures to see how they're interpreted by different cultures and to see if they are consistent or not. Okay, so again, other researchers like Ekman, for example, included the contempt and embarrassment, while others don't. Now, there seems to be a lot of agreement over most of these basic emotions that I showed you, particularly the one in common, the 6 ones that are in common between Ekman and Plutchik. But there is some sort of a disagreement or less agreement over expressions of surprise and disgust. Okay. And of course, culture is going to have something to do with this, where there's going to be some sort of culture training on what an emotion and expression should look like. Okay, and I have a bar figure that kind of makes that point in a second. Does that make sense? All right, so let's go through this bar graph together. The different colors are going to denote the different basic emotions that we have. Happiness, surprise, anger, sadness, fear, and disgust. The 6 ones where there is less disagreement over, okay? Not all 8 of them. And then on the x-axis, you have the percent of agreement. So the percent is going to be on the y-axis. And then on the x-axis, you're going to have among Western societies, non-Western but literate societies, and then isolated non-literate societies. Okay? So basically, if you show these pictures, to, here we have 20 groups of Western literate societies, what percent of agreement say, let's say it's a picture of a happy face, what's the percentage of people who say among all these 20 different countries, say that this is a picture of a happy face, is what we're looking at. Does that make sense? Okay, and then the white line in the bars here, that indicates chance level. So by chance, what are the chances that they would look at any picture and say this is happy? So really the critical comparison here would be how big or how tall is the bar beyond the white line. Sure. So the critical thing to look here when you're comparing to see which emotion there is more agreement on, kind of pointing to the fact that it's more of a basic emotion, is to see how tall that bar is beyond chance, beyond the white line. Does that make sense, Sasha? Okay. Okay. And so I'm going to say this is purple, but I think this looks purple from here anyways, blue, whatever. I'm not that good with differentiating colors, and things look kind of different on the projector, but dark blue one, okay? It's for happiness, and you see that for happiness, whether it's a Western literate society, whether it's a non-Western literate society, whether it's an isolated non-literate society, that all of them basically agree on what happiness should look like. Okay? Pointing to that, yes, happiness is a basic emotion and that it's biologically programmed. Okay, can you follow the logic there? Okay. Now, let's look at far right where I have two red arrows pointing at a couple of the bars. One at the baby blue or light blue, and then one at this mustard color. Okay? There's very little bit of the bar beyond chance level. Okay, so these two colors correspond to surprise and disgust, right? Remember in the previous slide I said there's less agreement over surprise and disgust, meaning that when we show pictures of surprise and disgust, we get less percentage of people agreeing, saying that, correctly pointing to the surprise picture and saying, ah, surprise, or to the disgust picture and say, this is a picture of someone who's disgusted. And literate, whether it's Western or non-Western society, agree actually on most of these basic emotions, indicated by how tall all of the bars are beyond chance. Can you see that for the two parts on the left? Okay, but for the non-literate societies, that there seems to be less agreement on what disgust and surprise look like. And what do you think that means? What does that mean? Why do you think there's a lot of agreement over what they look like in 20 Western literate and 11 non-Western literate? That's a lot. So what happened? Why do you think there's a disagreement then for these two? And what does that mean? Yes?
I think that in other cultures are in the cultures that are more tribal, maybe the ones that are say isolated, they don't really get that emotion discussed because there's not a lot of there's more equality in their society. They don't really compete for certain things like we do. They more work together and stuff, so they don't really experience disgust that much.
No, I can see what you're saying, but think about disgust is when somebody goes in the forest. The trees and the plants don't come with a label on the back of them saying a list of ingredients, yeah? So you have to have a mechanism that tells you whether what's in front of you is poisonous or not. And you taste something, most poisonous things taste bitter, and you're disgusted, you want to vomit it or you want to just spit it out. So disgust is indeed there. What we're saying here is not that they don't feel disgust, is that they, when they look at a picture of a disgusted person, or their own display of disgust is different. Okay? So what do you think that means? Yes, Sophia.
Is it because emotion is used, emotional expressions is used to communicate, and so because they're isolated, they've only got to communicate to each other, so that agreement about what disgust should look like is different because they're not being exposed to a wider group.
But why just disgust? If you're right, you're absolutely right that one of the purposes of emotion is to communicate. That's definitely right. But why does it only affect disgust, and surprise. Why not? I mean, the happiness is used for communication, sadness is used for communication. Why just these two? Yes, Victor.
They probably think surprise is more like anger. So they're surprised, or no, surprise is more like fear. So if they're surprised to see a wild animal coming at them, they'll think that's more of a fear emotion.
No, they have fear too. They still have, fear, and they still have agreement % over that. But think about the previous slide. I ended up with saying that there's going to be, yes, you're biologically programmed for basic emotions, and this pretty much shows that really pretty solidly. But also there's going to be cultural conditioning. And it turns out that at least for the case of surprise and disgust, that there's very much a cultural conditioning that goes with specifically these two. So perhaps even though this is Western and this is non-Western literate, they're probably literate means they're reading. So they're reading stories about what happiness should look like, or what fear and surprise should look like, and maybe that's why there's more agreement over it. So it may be the case that with disgust and surprise, that there's more cultural conditioning that is permitted for these two. Does that make sense? Delaney, do you have a question?
No, I don't think so.
Okay.
What do you mean by cultural conditioning? Like
So the way they grow up, the way they are shown how to display their emotions.
So just like the way that they express those two emotions are just different because the literate groups have like more like direction or.
Oh no. That they have been in all of them. There's going to be tutoring almost when the person is young on how to emote, how to show emotions.
So they just learn a different way to show them.
That they express these two emotions differently, in a way where it's not consistent with the other two groups. Okay, so as the previous 2 or 3 slides indicated, that one way to know about emotions and whether we have basic emotions is to look at facial expressions. Okay, and facial expressions are mediated by muscles, and as if you remember from previous chapters, there's going to be nerves called the cranial nerves that control and that are just dedicated for controlling facial muscles. Okay. We're going to have 2 categories of facial muscles. Ones that are superficial, so basically where 2 facial skins are attached. Okay? And that's going to be excited or innervated by facial nerve 7. So remember the cranial nerves? Okay? And then there's going to be deep facial muscles that are attached to bone. And that will cause more bigger changes in the face. So for example, when you're chewing something, the movement of the jaw. That's a much bigger change. And that's going to be innervated by the motor output of trigeminal 5. Okay? So the muscles around the eyes, the forehead, the mouth, all of that is going to be indicative of a facial expression and is going to be telling of what emotion the person is having. Okay. So one hypothesis, given what we know about facial expressions, which is the facial feedback hypothesis, it suggests that sensory feedback from our facial expressions can actually affect our mood. So basically, if you wear a happy face, you're happy. If you wear a sad face, you're sad. Okay? In essence, very consistent with the James-Lange theory. So, and one support for this hypothesis is that people who get a Botox shot, where basically they paralyze, let's say, the forehead, that they report also a reduction, a severe reduction in their ability to feel different emotions. Okay. So the intensity is lowered on all emotions as a result of not being able to move their facial expressions. Yeah, yeah. Okay. Okay, so in one experiment, what they did was they had people read comic books. And when they were reading the comic books, they had a half of the group force on a smile by holding the pencil like this in B, or force on a frown by kind of like holding it how it is in A. And people who forced on a smile while reading the comedy article, they actually reported finding that these cartoons were much more funny than people who did not force on a smile. Okay, so basically there's this feedback mechanism from like what the sensory or current state of our facial expression is back to how we feel and how it can affect our mood. Okay, so Darwin in the 1800s, so very long time ago, talked also about the expression of emotions in animals and how we also have basic emotions that are universal to all people, and kind of pointing, because they're universal to all people and they're found also in some animals, is that perhaps we have a common ancestor, non-human primate ancestors who also display these facial expressions. And indeed we do. Some of the non-human primates do express similar facial expressions, as I'll show you in the next slide. Now, about a century later, in 1982, Röntgen did show that some non-human primates do have some sort of expression of what looks like happiness or laughter in humans, called a play face. Okay? Which would be B, he's getting tickled. So this play face has been interpreted as homologous to the human primates, laughter maybe. Okay. And then in C here we have this kind of like showing of the teeth. It's kind of showing that they submit to a more dominant primate in that hierarchy, because they live in hierarchies where there's going to be a dominant one, less dominant one, and this here he's showing some sort of submission to a more dominant animal. Okay. And in rats and rodents, they've also shown that if you tickle a rat, that even though you can't hear it, but they have ultrasonic sounds that are analogous to laughter in humans. Okay. Okay. So evolutionary psychology is going to study these kind of things. Is that how natural selection shapes our behavior. And the two people, and I believe, a few years ago they were at University in Santa Barbara, I don't know if they moved or not, is Kosmides and Tubin. So, and so kind of similar to, I think what you said, Sophie, about emotions are important because they help people communicate. Okay? And also it acts as a motivation for people to adapt to the environment and to display behaviors that make them survive longer. Okay? And to actually make them fit in their ecological niche. Okay? To fit with their group, to cooperate with their group. So it's like a non-verbal language that they have. Okay, so now let's go back to the brain. So we know that if you electrically stimulate certain parts of the brain, that the person can feel an emotion. So we know that the brain is really important to emotions. And we know, Cannon and Bard alluded to this as well too. We also know, so this brain self-stimulation is something that's used in many different paradigms, and there are the areas in the brain that feel good when stimulated. And then since the first time it was discovered by Old and Milner that rats will continue to stimulate an area. So basically the paradigm goes something like this. You have a rat, okay, or any animal model in a cage, and they can press a lever, and that press of the lever is connected to a cannula that's inserted in the brain, and that releases a certain something, okay, or an electrode that is going to stimulate the area. So every time the animal presses the lever, it stimulates that area. Well, if stimulation of that area feels good, it's going to keep pressing the lever. Okay? In other words, it's going to keep self-stimulate. Okay? So we know that there's an area in the nucleus accumbens that releases dopamine, where rats will keep pressing the lever thousands of times a minute, will completely ignore cheese, even if it's California cheese. It will completely ignore everything that it has in front of it. It will just keep pressing the lever to get that self-stimulation of the electrode. Okay? And we also know that this pleasure center, this area that the animal will keep self-stimulating, is also involved in all addicted drugs. Okay, so beyond that experiment, they then went on a search for, okay, so what else other than this area are there also, would the animal be interested in self-stimulating? Okay. And we know that there is a bundle of axons in the middle of the brain, the medial forebrain bundle, that goes from the middle of the brain through the hypothalamus, that there's many sites in that bundle where if you inject an electrode there, that the animal will keep pressing the lever, meaning that they will self-stimulate. They'll be interested in self-stimulating that area. Okay? And then we already talked about the nucleus accumbens, that certainly animals will work very hard to do whatever it takes to self-stimulate or to get stimulation in that area, because it releases dopamine, and dopamine has kind of like this reinforcing kind of feeling to it. Okay, so here is what this midbrain bundle looks like. Okay, so do you see the medial forebrain bundle across all these three different arrows? So sites, all the red hot spots, these are all sites that when stimulated feel good, and that the animal will work very hard to self-stimulate. Okay, and then somebody did something that was pretty interesting, where they took off the cortex of animals. So decorticate the animals. D means taking off or undoing the cortex of the animal in dogs. And what they noticed is as soon as they decorticated, they separated the cortex from the rest of the brain, that something very interesting happened immediately. And that is the dogs displayed almost an immediate sudden rage. So that suggested that perhaps the cortex that was removed was controlling this rage, or was inhibiting this rage. Now another, sometimes instead of saying decorticated rage, we just say sham rage. Because it's not provoked, there's no stimulus that made the dogs angry, nothing made them angry, it was unprovoked, but then they displayed this sudden rage, indicating that there was something in the cortex that was removed that controlled this or inhibited this rage. Okay? Now, out of that research, a research on the corpse of people who died, who had some emotional problem, James Pate suggested that perhaps there's a system of interconnected areas in the brain, now called the limbic system, that are very important for emotional processing. And any pathology or anything wrong or disconnection in these different areas is going to give rise to emotional pathologies. For example, okay, the Kluver-Bucy syndrome, where parts of the medial temporal lobe, and more specifically, they found that it's really the amygdala in there, okay, which is a part of the limbic system that Pace talked about. When that is, for some reason, removed, lesions, what they found in monkeys when that happened is that they developed a syndrome called the Kluver-Bucy syndrome. And the syndrome is characterized by immediate emotional changes, and all of a sudden the monkey that was scared of snakes and fires, because monkeys don't like snakes and fire, is all of a sudden playing with a snake. And is a very tame animal. And they lost their sense of fear. So things that they previously were scared of, they're no longer scared of it. Indicating that indeed there are brain areas that are dedicated for processing emotion. And we know from lesion studies removing these different areas of the limbic system that more specifically the amygdala, which means almond, because it looks like an almond, when that's removed, that fear is severely affected as an emotion. So as in the case of the monkeys here with the Kluver-Bucy syndrome, they no longer feel fear. Very tame. Now that's very bad, because if you don't feel fear, although it sounds at the beginning, it sounds very something that is to be coveted for, fear is very important to tell you how you should act. So monkeys who don't feel fear, for the more dominant monkeys, they'll just go and fight with the big guy. And then they end up dying. Okay, so here are the different interconnected parts of the limbic system. Now, I do want to point your attention to the fact that different textbooks might include different parts in the limbic system. So just know the parts that go in your textbook, which is pretty much the mammillary area in the hypothalamus, the fornix, the mammillary body, the olfactory bulb, the amygdala for sure obviously has to be in there, the hippocampus. I've seen some books that do not include the hippocampus in there, but I think it should be. So all of these areas are these interconnected parts make up the limbic system. And limbus means border. Okay, because it's kind of like a border around all these structures below the cortex. Okay. So now we have many paradigms to study different emotions. And since we talked about fear, and because fear is probably one of the most studied ones, we certainly have paradigms to look at fear and to look at what happens when we interfere with a certain brain area and what happens to that emotion. So we could use things from psychology like classical conditioning, where you pair two stimuli, okay, one that naturally elicits a response and one that gets paired with it. Okay? So for example, an electric shock in rats will elicit an unconditional response of freezing. Okay? But when you pair that electric shock with, let's say, a sound of a tone, so the rat hears a tone, then shortly after they get a shock, and they go through many trials of that, then eventually the rat doesn't have to get shocked, that only hearing the tone is going to elicit the freezing response. Make sense? Using paradigms like that, we know that, which is called the fear conditioning paradigm, we know that the amygdala in the temporal lobe is really important for fear conditioning. Meaning if the amygdala is taking out, or it's lesions, that the animal does not learn to condition or to associate the sound of the tone with the shock to elicit the appropriate response. Okay. So let me show you what the paradigm looks like. Here, the grid. Here is a cage with a grid on the bottom, and then here on the bottom here I have measurements of the blood pressure and the amount of freezing. Okay, for all three different situations. when the rat is trained to associate the tone with the electric grid, as in the last one on the right here, that the rat, as soon as it hears the tone, without even being electrified or anything like that, it starts freezing. Okay? And if you look at the bottom, B and C look exactly the same. That the blood pressure is increased, the blood pressure is increased. The duration of freezing is the same. So they have learned to associate, or in other words, they have successfully been conditioned, fear conditioned. Okay. Now, so fear conditioning, or the emotion of fear, has to get to the amygdala. But there's almost two ways to get to the amygdala. Okay? There's the low road and the fast one, which goes straight from like the sensory information you gathered that from the environment to the thalamus and straight to the amygdala. That's going to be unconscious. It's going to be very fast. Okay? Sometimes you have an emotion and you act in a certain way, and then a few minutes later you realize you're like, okay, back, your consciousness is back, and you start to interpret the situation. Which, if you think about it, is really important when you're out there in the forest, and sometimes you have to make decisions really quickly, and everything takes time. So you can't wait for the information to go to your thinking system, back to the amygdala, back feedback from the thinking system. That might be too long, and it might decrease your chances of survival. But sure enough, when you do have that time, there's another high road that does go through your cortex and then to your amygdala. Okay? So we have two. You gather information about the stimuli in the environment. It goes to the thalamus. Okay? And then from the thalamus, it can go very quickly, shortcut, slow road to the amygdala. And more specifically, so the amygdala is a collection of nuclei. And more specifically to a nucleus, they are called the central nucleus. And then the central nucleus is going to evoke the autonomic nervous system, hormonal release, all that stuff that goes with that emotion. Or it can go to your sensory cortex, the memory center, the hippocampus. Okay, so in the past, this big hairy thing that's coming at me, well, I know right now I'm not in a forest, so it can't be a bear, it's just my partner or something. Okay, so, and then you are not going to run the other way, or maybe you will, I don't know. Okay, but the point is that there is one where that you're going to have time to think, which is conscious, which is going to have, go to all these steps, and then the amygdala. So both of them will end in the amygdala. But there's one that's going to be fast and unconscious, and there's going to be one that's a little bit longer and more conscious. Does that make sense? Okay, I'm going to stop here.